Welcome everyone to the 13th annual John H. and Cynthia H. Schultz Lecture in Energy, featuring Dr. Stephen Chu, who will be addressing climate change and innovative paths to a sustainable future. I'm Alice Madden, the Executive Director of the Getches Wilkinson Center for Natural Resources, Energy and the Environment here at Colorado Law. I know that the Schultz's daughter, Cynthia Howard, and her family are watching tonight, but with well over 400 folks registered, I know that all of you are not familiar with the Schultzes, but I can assure you they were the kind of donors any university could dream of. Their generosity went well beyond their numerous monetary gifts to the school, like this endowed lecture series, scholarships, loan repayment programs. John in particular made deep connections with many of our students and faculty and was a friend and advisor to several deans. Cynthia passed away in 2011, and sadly, John passed away last April. And because of the pandemic, we've not been able to celebrate his life. So thank you so much for allowing me a moment just to tell you a bit about John Schultz. He was born in a charity ward in Denver, Colorado. He began working at age 10 and went on to build a very successful energy law practice. But he was not all work and no play. Like a true Coloradan with a joie de vivre, John carved out time to enjoy his family and everything the great outdoors in Colorado has to offer. But I think perhaps most importantly, John believed that you must always be willing to give back to the people and places that helped you get where you are. And he always instilled in the students he met with the importance of paying your own good fortune forward. A remarkable man, a true inspiration, who will dearly be missed by all of us here at Colorado Law. Our dean, James Anaya, was very sorry he could not join us tonight, but he wanted me to both welcome Dr. Chu and extend his personal thanks to the entire Schultz and Howard families, because their generosity allows the center to invite leading minds from the country like Dr. Chu to address emerging issues in oil and gas, energy, natural resources, and climate change. So now I'm going to hand this over to Professor Sharon Jacobs to introduce our distinguished guest. But first, let me share a little bit about my colleague. Sharon came to CU in 2014 after several years practicing energy law and regulation in Washington, D.C., and after 2 years teaching as a fellow at Harvard Law School. She is immensely popular with our students, and her scholarship, which has been published or is forthcoming in the Harvard Law Review, the Yale Law Journal, the Columbia Law Review, and other publications, has already received national recognition. And tonight, I'm very honored to announce that Dean Anaya recently named Sharon as the John H. Schultz Energy Natural Resources Law Fellow. So congratulations, Sharon. It's a well-deserved, very high honor. Really simply put, Sharon is just one of those bright lights, the kind of person you are lucky to work with and to learn from. So on that note, I'll hand it off to Sharon. Enjoy everyone tonight. And again, welcome Dr. Chu.
Thank you so much, Alice, for that overly kind introduction. And may I say it's been my pleasure to collaborate with you over the past several years to further the excellent work of this center, which is named for our late Dean, David Getches, and our dear colleague, Charles Wilkinson. Good evening to everyone, and thank you all for joining us, at least virtually, here in Colorado for tonight's Schultz Lecture. I'm delighted, but not at all surprised to see such a large audience for this event for Dr. Chu's remarks. We will save 10 minutes following the lecture for Q&A, and please use the Q&A function at the bottom of your screen to pose your questions. I will be collecting those questions to pose to Dr. Chu following the presentation. Now, I would be remiss if I didn't say a big thank you to Sean Labar, the Deputy Director of the Getches Wilkinson Center, for his hard and as always meticulous work in putting together this event during unusually difficult times and under unusually difficult circumstances. Thank you so much, Sean. This lecture series is in its 13th season, and it's due to the generosity of John and Cynthia Schultz and the continued support of the entire Schultz family, including Cynthia and Dave Howard, who are here tonight, and their children, Michael and Alyssa. They are the reasons we can bring you tonight's lecture free of charge. I remember the first time that I met John. It was at a dinner following a Schultz lecture given by then Governor John Hickenlooper. And what struck me during our initial conversation was how much he cared about our students and how much he cared about their future and about the state of Colorado, and more generally about education and service more broadly, the idea of giving back to our community. This lecture series is very much in that spirit. It offers our students, the law school, the broader university communities, and our friends and partners across the state, and now around the country and the world, a chance to hear from the leading energy thinkers of our time. And I am thrilled tonight to introduce our Schultz lecturer, Dr. Stephen Chu. Dr. Chu is the William R. Kennan Jr. Professor of Physics and Professor of Molecular and Cellular Physiology in the medical school at Stanford University. Dr. Chu was the 12th US Secretary of Energy from January 2009 until the end of 2013. And as the first scientist to hold a cabinet position and the longest serving energy secretary, he recruited outstanding scientists and engineers into the Department of Energy. He began several initiatives, including the Energy Innovation Hubs Initiative and ARPA-E, the Advanced Research Projects Agency for Energy, and was personally tasked by President Obama to assist BP in stopping the Deepwater Horizon oil leak. Prior to his cabinet post, he was director of the Lawrence Berkeley National Laboratory, where he was active in pursuit of alternative and renewable energy technologies. Dr. Chu is a co-recipient of the 1997 Nobel Prize in Physics for his contributions to laser cooling and atom trapping, and he has received numerous other awards. He's a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, and is a member or foreign member of leading societies and academies across the globe. Dr. Chu received an AB degree in mathematics and a Bachelor of Science degree in physics from the University of Rochester, and a PhD in physics from the University of California, Berkeley. He's also in possession of 32 honorary degrees, one of which comes from Harvard University. And in fact, Dr. Chu and I have a connection that he is not aware of. He was the commencement speaker at Harvard in 2009, which was the year that I graduated from law school there. And although the flu sadly kept me from attending that address in person, I watched from my apartment across the street and followed along online. And Dr. Chu, you spoke a line in that talk that I will never forget. You said, "The climate problem is the unintended consequence of our success." And it's a line that has guided me in my energy law and policy work since then, the knowledge that we are responsible for the consequences of our achievements. So it is with great personal pleasure and gratitude that I say welcome, Dr. Chu, and thank you for taking the time to address our students and the broader Colorado law community tonight.
Okay, thank you for the very generous introduction. And without further ado, I'm very happy to be here and talk to all of you. I'm going to share my screen and let's just see if this works. Let me just try this. And you see everything? Okay, great. And then I'm going to see if I can minimize that. Anyway, you don't see the little thing on the side, do you?
We do not.
Great. Okay, so I'm going to talk about climate change. I'm just some stuff that you, I'm sure, know a lot about, but I just want to remind you of it. And then innovative paths to solutions. So let me begin. And let me see if I can do that. And then apparently this is not working. Okay, so I'm gonna have to, okay, great. All right, so, all right, climate change and where we're heading, and then I'll talk about the science and technology. This is a history arbitrarily chosen to be since 1 AD of the level of CO2 in the atmosphere around the world. And you see it kind of meanders around in a pretty flat region around 280 parts per million. And then suddenly it starts going up. And roughly speaking, in 2021, 2020, we're at 415 parts per million. Now, what does this due to? Well, if you do some arithmetic, and you say, how much CO2 have humans emitted in this time? And agrees with the rough estimate of human CO2 emissions, minus 1/2. Because when you emit CO2, roughly half of it within 5 or so years gets absorbed very quickly by land, vegetation, and the oceans. And so it agrees quantitatively with our understanding of how the Earth deals with CO2. But it's also startling to realize that if you look at the isotopes of carbon, in particular carbon-14 and carbon-12, this gives you human fingerprints that this rise in CO2 is very different. Now, how does that work? Carbon-14 is radioactive. It's made in the upper atmosphere of the Earth due to cosmic rays, and converts nitrogen into carbon-14. That carbon-14 diffuses down, is part of the biosphere and everything else on Earth. And you and I have carbon-14 in ourselves. And suppose, eventually I've been told that all good things come to pass and we die. And just imagine we're put in a coffin that's sealed from the Earth's environment, fossilized and sequestered. But people dig us up many carbon-14 lifetimes later, it's 5,000 years, so 50,000 years, there's no more carbon-14 in us. And we put ourselves in a power station, burners for fuel, for energy. And all of a sudden the carbon released is just carbon-12 and carbon-13, no carbon-14. If that's massive enough, you dilute the amount of carbon-14 in the atmosphere. And that too agrees quantitatively with what is happening. So this rise in CO2 is really due to carbon that has been sequestered for a very long time. If you have carbon in a tree, the tree grows up, dies after hundreds of years, tens of years, even thousands of years. That carbon gets recycled typically within a carbon-14 lifetime. So this time it's very different. Now, if you look at going back further in time, not 1,000 years, but 800,000 years, and you say, well, Neanderthals are wandering around the world and the last warm period is over here. And you ask yourself, and this is humans, this is why it's so important to point out this time it's different. If you look at the carbon dioxide, the methane, and the temperature, you see that they go up and down. But this carbon now has skyrocketed up here and very, very different. So there's other things we notice. You can ask, are glaciers melting? Is the sea level rising? The short answer is yes. You can go to glaciers. Let's say Muir Glacier in Alaska in 1941. There's a picture of the glacier. You can come back in 2004, you see a very different picture, but this is one glacier. And the satellite data over the last couple of decades show that this is not just one glacier, it's happening all over the world. And startlingly, very worrisomely, the ice in Greenland and Antarctica are melting far faster than we thought they would be melting 20 years ago. And so this is another alarming thing that's going on. Now, this is from so-called carbon scenario budgets from 1980 to 2010. We're in this little red dot here. Well, we're now in 2021, so it's a few years old. And on the y-axis, emissions from fossil fuel, land use changes in gigatons, billions of tons of CO2 a year. All those little lines are different scenarios. And this stuff on the right-hand side are, if you have carbon emissions during this whole time, what's the predicted temperature after you're done with these emissions by the year 2100. And you see that in order to stay below 2 degrees, something has to happen. The carbon emissions of everything in the world has to go below 0. Okay, let me say it again, it has to go below 0. That's not just carbon from power plants, that's carbon from everything, all over the world. And so that requires, if you want to stay below even 2 degrees centigrade, but 1.5 degrees, it requires negative emissions by 2080. So in this scenario that I would draw, it's a compromise scenario, it looks like we're going to be at 2.5, 3 degrees. Let me remind you that during the last warm period, interglacial period, that's the last warm period, 130,000 to 116,000 years ago, the mean sea level was 6 to 9 meters higher than today. But if you go back and say, what was the Earth like with the carbon dioxide concentration of today? And that you have to go back 3, 4, 5 million years ago. The intensity, the energy hitting from the sun is about the same. The continents were all in the red place. So those are not factors. And when you look at the, yes, here it is. When you look at this period of time, 3 to 5 million years ago, the temperature was 2 degrees warmer and the sea level was 10 to 20 meters higher than now. So if you believe that history can be some indicator of what the Earth might be like when it's roughly the same in all the other major criteria that govern the temperature, this is even more worrisome. All right, so I think my battery is coming down. So let me try this again. Okay, so anyway, so these are some of the things. We're seeing that water aquifers are being depleted in many parts of the world. We see increased droughts, heat waves, water shortages. California, fire seasons now 8 or 9 months out of a year, and rising seas. All of this is projected to create climate refugees, not in the millions, but in the tens to hundreds of millions in the coming years. And for example, this is a map of where there's water stress in the world today. And you see that when you have a change in climate, the rains are not going to come when you want them to come. They're going to come, there will be actually more rain, but the drier places get drier, the wetter places get wetter, and winter and spring snows might turn into rains. And so the water storage system in the form of snow is also going to be at risk. So where are we going? This is again from 1750 to the present time. And you notice on the y-axis, I'm plotting cumulative worldwide emissions. Well, why cumulative? Why? Because all the other graphs I've been showing are emissions per year. And the reason it's cumulative is when you stick the CO2 in the atmosphere, remember I told you that half of it gets rapidly absorbed by the land and oceans in increased plant growth and in inorganic absorption of carbon dioxide in the oceans, makes it more acidic. But the other half circulates between land and ocean, and the mean time of circulation is estimated to be about 10,000 years. So that's a very long time. And so if you're looking at what's going to happen in the next 100, 200 years, 50 years, you're going to say, unless you can figure out a means of getting rid of the carbon dioxide that's in the atmosphere and circulating around, you need to talk about cumulative emissions. So here's where we are. The dotted line is where you begin to stray into a significant probability of getting to 2 degrees or higher. And we think based on our current rate, we will pass that within a couple of decades. Okay. It's also important to notice that most of the emission has occurred only over the last 65 years. And although Yogi Berra did not say this, he could have, but it was reputed to have been said by a Chinese philosopher that said, if you don't change direction, you will end up where you're heading. And so we are heading to a warmer world. All right, so how do you stop greenhouse gas emissions and all greenhouse gas emissions? And you start by capturing CO2 from local emitters, and the largest emitters besides power generation, and I'll get to the really largest emitter in just a minute, would be transportation, cement, production of chemicals and plastics, iron and steel. This is an old slide. Cement is now 8% of worldwide carbon emissions. So an amazing thing about what we do is humans plant a lot of food, and we eat the food, and we raise crops for animal feed. And if you look at the total amount of carbon the plants take out of the atmosphere, I'm not talking about Brazilian rainforests. I'm talking about plants that we grow every year for ourselves and the animals we eat. It actually is about double the amount of CO2 we emit. The only trouble is 99.8% or 9% of that gets recycled. So if you could figure out how to take all this plant material, turn it into useful products, sequester the rest of the carbon dioxide, you have a great negative carbon sink, which would be wonderful. All right, let's talk about science and technology. All right, the first thing I want to remind you, and this is a saying, one of my favorite sayings by Sheikh Yamani, who was a former Saudi oil minister, and he said, the Stone Age came to an end, not for lack of stones, and the oil age will end, but not for lack of oil. And what did he mean by that? Is it, well, we went from the Stone Age to the Metal Age because we went to better solutions. And also unsaid is, if you don't find better solutions, there's a likelihood that the oil and natural gas, this is trillions of dollars worth of stuff underneath the ground, would come out and be used. So it's very important that we find better solutions that are going to be competitive and better than competitive with oil and natural gas. All right. So what's the biggest greenhouse gas emitter of all the sectors? It's not electricity generation. It's agriculture and land use. About 28% of this greenhouse gas emissions comes from that, but it's actually higher than that. So in this IPCC summary report, you see the orange down here, 59% of greenhouse gases is from carbon dioxide, fossil fuel, industrial processes. You see CO2 from forestry and agriculture in this dark orange. You see methane, but more than half the methane is not due to methane for energy in the power industry. It's actually due to methane from animals and crops. Then we have N2O. What is N2O? Well, this is mostly due to fertilizer runoff, excess fertilizer runoff, which is a potent greenhouse gas. And then methane, of course, is a very potent greenhouse gas. So this is what we have. More than half of all the habitable land in the world is used for agriculture and grazing. So we've co-opted a large fraction of the available earth for ourselves. This is a scale of biological engineering and geoengineering that I want you to appreciate. For example, since I'm a professor, I'll give you a little quiz. There are two types of corn. And which is the native corn and which is the corn we eat? We've altered the wild corn so it's not recognizable. We've induced these plants to grow tremendous amounts of seeds with starch and sugars around them that they had no business growing, because they said, I just need enough seeds to reproduce. And all of a sudden we've got, this great corn that we eat, okay? What about animals? These are the life cycles, the full circle are the life cycles of animals, beef, pigs, broiler chickens. And we've engineered these animals so they're slaughtered in a very small fraction, that's the red stuff, from time of birth to the natural life cycle. For example, pigs are slaughtered typically 24 weeks after birth, but these pigs grow so rapidly that the average weight of a US pig at slaughter time is 280 pounds, 24 weeks. And so these livestock have been bred to optimize early growth in a very small fraction of their natural life cycle. Let me give you an example. There's turkeys that have been bred. These are the ones you can buy at Safeway, 14 pounds at Thanksgiving. That's 14 pounds without the head, the feet, and most of the guts and feathers. And they're slaughtered about 3.5 months since hatching. What's remarkable about these farm-bred turkeys is they're so artificial because they're so breast heavy, because the public, the American public in particular, likes white meat. So they can't mate. So they're actually mated by artificial insemination. So these are the turkeys we eat. They look a lot different than wild turkeys of unknown ages. We don't know how old these are. I can assure you that this wild turkey is about 8 years old if it's Wild Turkey 101. But the other turkeys, they look different. All right, now this is the next few slides are from a friend of mine, Pat Brown. He used to be a colleague of mine in Stanford University in the medical school in biochemistry. Very distinguished scientist, member of the National Academy. And he called me up one day years ago and said, Steve, you inspired me. I quit my job. You left your job to become Secretary of Energy, so I thought I should do my part, but I'm just a biochemist. You know, first I said, Pat, what did you do? You quit. You know, what are you going to do? And he said, well, you know, I'm a biochemist. I know chemistry. Is it possible that I could do something to get a substitute for the animal meat we eat that was much more friendly to the world and much less carbon and water intensive? And so he founded a new company called Impossible Foods, which makes burger-like materials and soon to be pork-like materials out of things, soy and other materials. And in this talk he gave at the AAAS, the American Association for the Advancement of Science this year, he said in this first slide, 10,000 years ago before Christ, if you look at the animals in the world, you have here humans. There are 0.2 million tons of humans on the earth during this time. There's 0.2 million tons of domesticated cattle or oxen or things like that. And there are 300 million tons of wild animals. Well, that's 10,000 years ago or 12,000 years ago. Where are we today? Wait a minute. Here we are. Nowadays, the cattle consists of 1 billion tons of animal mass. We're 420 million tons of animal mass. All the other wild animals are only 90 million tons. All right, so let me go back. We used to be roughly 300 million tons of animals, and now we're much more, and the number of wild animals has shrunk. And we've replaced most of these wild animals with animals we eat, most notably cows. And so if you look at the cattle, the weight of the cattle outweigh all terrestrial vertebrates by a factor of more than 10 to 1. The meat consumed annually by people outweigh all the wild animals and vertebrates by 6 to 1. Every year we consume more than 6 times more weight in terms of animals than exists in the wild. And Pat goes on to say, and even begun to say about the water consumption, water pollution, public health impacts, and displacement of indigenous populations. All right. So if you look at the annual emissions in the world, again, from 1751 to 2015, what you see is this light tan is the EU 28. Great Britain was still part of the EU. The biggest emitters are the United States and China, and then this is the rest of the world in various slices. But if beef and dairy cattle were a country, at 2 years ago, their greenhouse gas equivalent emissions per year would be more than any other country except the United States and China, including the entire EU 28 combined. So again, let me remind you, if you take all the livestock mass, mammal mass of livestock stuff we eat and humans, it's actually 90% of all the mammal mass in the entire world. So we have really changed the world, and we use a lot of our land use to actually feed the animals we eat. So what Pat Brown said is, is it possible to make out of soy products and other vegetable-like products something that tastes like a hamburger? And the two leading companies are Beyond Meat and Impossible Food. And there's a lot of very sophisticated chemistry in this Impossible Food burger. They actually use a hemoglobin-like molecule that is derived from the soy plant to actually make it taste like blood. And then they said, well, let's try other forms of hemoglobin, like animal hemoglobin. And then they did blind tasting, and they found that people actually like the blood taste of the hemoglobin-like molecule that comes from a soy plant. But they found they couldn't extract enough of this because it's in the roots of the soy plant. And so they finally said, forget it. We're going to tell yeast how to grow this hemoglobin-like molecule using molecular genetics. And they harvest this flavor from yeast. So, and other pretty fancy chemistry. Let me also say, not only have we changed the land environment of all the wild animals, we've also changed fish. About 90% of all the big fish in the world are gone. This is the global wild salmon catch from 1950 to 2010, and you see it's just dwindling. What do we do? Well, if we want protein, is it possible to make salmon that can grow? And of course, you know about salmon farms. They have pollution issues, so that definitely has to be cleaned up. But there's also some modern science that says, if you change the salmon, so you put in salmon genes from other salmon genes, so it's not a weird gene, it's all from the same fish and an ocean pout, and then you can change the salmon so that they grow all year round. And so you see here two salmons. One is a natural wild type salmon, and the other is this genetically modified salmon. Now it took 20 years for the FDA to approve this. But the conditions are you can only grow these salmon in sealed tanks where the water discharge from the sealed tanks have all sorts of filters to make sure that the DNA from this modified salmon does not mix with the DNA with other fish in streams or lakes or get to salmon. But this is something that we have to consider, given that we have a world of about 7.7 or 8 billion people going to 11 billion people by the end of this century. All right, but you can actually go to plants, and an exciting new development is that you can breed microbes, genetically modified microbes, that begin to have symbiotic relationships with the roots of corn plants. And so there's a company called Pivot Bio in the Bay Area where they coat the microbes on seeds. The farmers plant the seeds. This has now been deployed for a couple of years. And the idea is that you use less fertilizer because half of the nitrogen actually comes from the microbes fixing nitrogen that is absorbed by the soil, and it goes into plants. So this is a very nice relationship because the plant says if it's hungry, it says, feed me. It sends out little chemical signals to the microbes and they feed the plant. And the results are pretty startling because the plants, instead of having massive doses of fertilizer once or twice in their lifetime, they're actually fed when they feel hungry. And you see on the right-hand side, the corn with the genetically modified microbes, and you see corn in some other plantings. So now you've got to make this so that it is adopted by farmers. The only way you can get it adopted by farmers is you're going to make it so that it's more productive for them to buy the special seeds. But so far, we haven't even touched the corn plants. And the hope is we can do this not only with corn, but wheat and rice and all the grains to make them self-fertilizing, or at least a large fraction of it self-fertilizing. You start with nitrogen first, but you go on to phosphorus and other materials. So, all right. Now, I'm sure all heard of the great progress in solar and wind, so I'm not going to talk about it, but except to remind you that the price of solar energy has gone down 50-fold in the last 40 or 50 years, more than 10-fold in the last 10 years. Wind has gone down dramatically as well, and they're both expected to reduce in cost by another factor of 2. And in many parts of the world, solar and wind will become cheaper than fossil fuel. So this is great. And the cost will continue to decline to where many of the oil companies think by 2030, 2040 at the latest, the average price of renewable energy, solar and wind, will be less than 1 cent per kilowatt hour to generate. Right now, in many parts of the world, it's greater than 5 cents a kilowatt hour. This is all great news. However, it has to be significantly less expensive than fossil fuel, because fossil fuel has the virtue that when you feel like it, you just turn on the power when you need it. And you can't do that with solar and wind. So the full cost of renewable energy, not at the 10 or 20% level, but at the 50, 60, 70% level, have to include all the other stuff, the backup energy generation, energy storage, enhanced transmission and distribution system. The good news is, since renewable is going to get cheaper, and since all these other things we need are going to get cheaper, this is actually an achievable goal. Let me talk about energy storage. So here is a picture of my favorite battery. How does it work? When the wind blows, you pump water. It takes energy to pump water out of a well. When you want the water, you just open up a valve. And so this is a form of energy storage that's very inexpensive. And in fact, raising water up a hill or out of the ground into a water tower turns out to be, if you have an existing dam, the cheapest form of stored energy in the world. And it is the most common form of stored energy in the world. More than 95% of all the stored energy in the world is in the form of hydroelectric power. And so what do you mean by pump storage? It's very simple. You have an upper basin dam and you have a lower basin dam. The lower basin, if the upper dam is a reservoir, the lower one could be 1/10, 1/20 of the upper reservoir, even less. And so when you want to generate electricity, you just let water flow through a pump turbine, turns the generator, and off you go. When you have excess electricity, it turns out you can design these pump turbines and the generator becomes, you use electricity to pump the turbine in reverse, and it actually pumps water back up the hill. Remarkably, if you have a couple 100 feet, 150 feet of height, it turns out that the round trip efficiency of letting water come down through the dam to spin the turbines and then pumping it back uphill is about 85% efficient. That is more efficient than today's utility scale flow batteries. So actually pump storage is highly efficient. I mean, it's not as high efficiency as the lithium-ion batteries that we use in our cell phones and electric vehicles. That could be in the middle 90s efficient, but it is more efficient than what are going to be considered as flow batteries for utility scale storage. The scale of these things are pretty big. This is what a turbine looks like, a hydro turbine. And this is the variable speed generator, but let me convince you how big these things are. Those are people, those little things below are people. Now, how do you make this more deployable and everything? You have to generate these in similar, identical sizes, but the only trouble is many people do not like hydropower, and so that is an issue. Okay, so what is the challenge of energy storage? Suppose you set as a goal that you want to run the United States on 80% renewable energy. That would include hydropower, solar, and wind, a little bit of geothermal energy. How much energy storage would you need roughly? And so in this article over here, this was analyzed, and it was a economic analysis. And it turns out in the middle of this, if you want 80% of power in the United States to come from clean, renewable energy, it turns out you need some tens of hours, okay? Tens of hours, well, that would maybe 100 hours. That sounds like nothing, but no, this is 100 hours of energy storage for the entire system of the United States. And so what does that mean? It means you need on scale of 10,000 gigawatt hours of energy storage. How much gigawatt hours of energy storage do we have today in the form of chemical batteries? A couple of gigawatts. So we're now at roughly 2 gigawatts. We got to get it to 10,000, but the price is prohibitive, because the estimate of what you would need if you wanted to keep energy prices within 20% of what they are today and use energy storage just to 80% renewables, not 100%, it has to be about tenfold cheaper than the batteries we make today. The price of utility scale batteries will go down by threefold, but they will have to go down by another little bit over threefold in order to achieve that. So this is a real issue. We don't have the technology, that's certainly not in the next 10 or 20 years that we foresee. So now, and we're not even talking about 100% storage. So the rest of the energy has to come from energy on demand stuff. And we only have two choices. That's fossil fuel or nuclear. All right. There's other forms of energy storage rather than chemical batteries. You can take electricity and you can turn it through electrolysis into hydrogen. You can have other sources of power and excess energy. You can turn this all into hydrogen. But then it requires energy. The conversion of electrical power to hydrogen is not that good. And so you're going to lose a lot, and then it costs a lot. You have to invest in electrolysis plant. Nevertheless, people are beginning to look at this because they're saying hydrogen could be a sort of a battery. You can store the hydrogen under salt caverns, things like that. It potentially can be used for transportation as well. And so we'll see how it evolves, but at least in some areas, hydrogen will be an alternative fuel. For example, in centrally fueled stations, in forklifts, hydrogen is already starting to be used as a fuel. And I'm not going to go into this catalysis of water, but I'm going to say that the real goal of energy storage is you take carbon dioxide from power plants and cement plants and steel plants and everything else, or from the atmosphere, and you take water, which, by the way, if you burn hydrocarbons or fossil fuel of any sort, you make carbon dioxide and water. But let's go in the reverse. So you have some form of clean energy. You can do thermochemically, electrochemically, biochemically, anything. And what you want to get is, starting point is hydrogen and CO, but you don't want to stop there. In the end, you want to make hydrocarbons, liquid hydrocarbons. Why do you want to make liquid hydrocarbons? Because they're very, very dense in terms of energy density per unit weight, energy density per unit volume. Liquid hydrocarbons are amazing. They have the highest energy form of density, except non-nuclear form of energy we know of. And so the reason oil is so good and why gasoline and diesel fuel are so good is because of its high energy density. This is a super tanker, and it's transporting crude, let's say where you have oil abundant reservoirs of crude. And so if I ask how much does it cost to ship and store oil to halfway around the world, in terms of how much it shows up in the gasoline pump, it turns out it's 2 cents a gallon. That means the cost of gasoline, the cost of shipping crude oil, storing it on site, in countries that will then refine it is an incidental cost. And so think of these super tankers as intercontinental energy transmission lines. And so what we now have before us is if you can take clean energy where it can be made very, very cheaply, where there's lots of wind, lots of sun, and most of the world doesn't have lots of wind, lots of sun, convert it into a liquid hydrocarbon, then you can stick it on a tanker, ship it around the world, and store it, and so that the country also has energy security. So this is, and we would also use this in airplanes and other vehicles, especially heavy-duty vehicles, where when you're pumping gasoline into a truck, you're pumping in 5 megawatts worth of energy into a truck. And that compares to the Tesla fast charge system, which is 140 kilowatts, 0.14 megawatts. So liquid fuel is pretty good stuff. All right, let me talk about electric vehicles. There are a few percent of new car sales today, and this optimistic, but I think we'll get there. Bloomberg New Energy Finance projection of a couple of years ago, they said by 2040, electric vehicles, light duty electric vehicles, will be more than half of new car sales. That's great news. The bad news is 45% of them will be internal combustion engine cars, which have a 15 to maybe 20-year lifetime. So if we do this and follow this optimistic path, we're going to see that the conversion to electric vehicles is not going to really happen for another half century. Now, let's talk about another conversion. Let's roll the clock back to the turn of the other century, from the 19th to 20th century. And on the left-hand side, I show you a picture of New York City, an Easter parade on Fifth Avenue, and you see all the people dressed up in their finery. And down Fifth Avenue, a lot of horse-drawn carriages. 13 years later, this is what Easter parade looked like in New York City. Okay, there was one motorized vehicle in the year 1900, and there's one horse-drawn carriage. This was the fastest technological change we've ever witnessed. And even though it required this whole new infrastructure, oil gasoline supply chain, you need better paved roads, repair shops, everything. It went really quickly. And the reason it went so quickly is it was spurred by a serious environmental pollution problem. And what was that problem? Well, the problem was in New York City, in 1880, there were 160,000 horses in Manhattan and in Brooklyn, and they were producing 3 to 4 million pounds of horse manure a day. You couldn't help it, notice it. It was ankle deep in many places. The stench was getting overwhelming. And so along comes a poopless carriage, and people gravitated towards it very quickly. Now what we see in gasoline and diesel vehicles is emission, smog, if you will, and nitrogen oxide and particulate matter. And this is Beijing maybe a few years ago on a bad air day. And what we found in the last decade and a half is that small particulate matter, so-called PM2.5, or particles less than 2.5 microns, is very, very deadly. For every 5 micrograms per cubic meter of these particles, there's an 18% higher chance of getting lung cancer, according to this large epidemiological study of 2013. It's being followed up with even larger studies, and the numbers are roughly the same so far. Okay, so 5 micrograms per cubic meter, 18% higher chance of getting lung cancer. Well, the average air in Beijing in 2016 was 76 micrograms per cubic meter. But it's worse than that, because actually lung cancer is only the 3rd biggest killer from PM2.5. It's coronary disease and stroke. Just like cigarette smoking. In fact, cigarette smoking has the same PM 2.5 small particles, and believe it or not, the same carcinogens are found in cigarette smoke as found in these particles as well. And so the World Health Guideline currently is 10 micrograms per cubic meter. It's considered, if you're below that, you're considered not a problem, clean air. And so there's an intense debate going on because of the economic repercussions, but you probably don't consider a 36% high chance of getting lung cancer as clean air. So here's where we are. There's other forms of energy storage that are being considered heat storage. Like I talked about hydrogen, I talked about pump storage. So far unproven, but it has potential, and we're looking at everything. I'm jumping around a little. I don't know how my slides got out of order, but batteries, lithium-ion batteries for electric vehicles. There's a fear that we may run out of lithium, or as electric vehicles become very popular, become the dominant choice of light vehicle transportation, that the price of lithium can go through the roof. That is certainly true of cobalt. We've got to design batteries that use no cobalt whatsoever, but it turns out that lithium is about as abundant in the Earth's crust as nitrogen, which is pretty abundant. It's just that you can't extract it very efficiently. And so in a paper published in 2020, this is Chung Lu, who's now an assistant professor at the University of Chicago, did some work that figured out how to extract efficiently lithium from seawater. And if you can do this commercially, you've just increased the source of lithium by 5,000-fold. That's not to say you don't want to recycle lithium, you still do that, but at least it takes care of the lithium supply for a couple thousand years. Okay. We want to get better batteries. I'm collaborating with Yishui at Stanford, who's a big battery guru. And I mentioned lithium is not going to be a problem, but you want to actually go to what we think is probably an ideal battery of lithium and sulfur. So instead of the cobalt, nickel, manganese batteries we now use, you get to sulfur. Why? Because sulfur is super, super cheap. And the other thing that is very much on our radar screen, the radar screen of anybody who's doing advanced research in batteries, and even battery companies and OEMs, automobile manufacturers, is that you want to have the batteries be able to charge much more quickly than you can today. And I think probably within 6 to 15 years, it's hard to really predict, we will get batteries so that if you have a higher energy density battery with a 350-mile range, that you can put 200 miles worth of stored electrical energy in that battery in 5 minutes. Now, if you can do that, then you go back to a service station model. So if you're on an interstate or you're driving around, you pull up into a service station and you stick a super fast charge into the car. How fast is super fast? Well, about 3 times faster than today's Tesla. But you can do this over and over again, so it doesn't wear out the battery. The Tesla fast charge does wear out the battery. And so this is very much on the horizon. And if once you have 200 miles in 5 minutes, so to put it in terms that people understand, the battery lasts longer than the human bladder. So if you're taking a long road trip, you're discharging yourself, the car is charging itself, takes about the same amount of time. You're okay with that. Turns out the gasoline stations want customers to hang around for 3 or 4 minutes, maybe 5 minutes. They don't want them to hang around for 10 minutes. Why 3 to 5 minutes? Because they make much more money selling candy and soda and cigarettes and all that stuff in their little quick marts than they do gasoline. Just like automobile the money is made in servicing automobiles, not in the selling of the car. Just like in copying inkjet printers, the money has nothing to do with the cost of the printer. It's always in the inkjet cartridges. And so one of the real advantages of electric vehicles is the maintenance goes way down. And the automobile manufacturers, and especially the dealers, are petrified that if electric vehicles begin to be the popular form of transportation, they've lost their money making. I've got an old internal combustion engine car. It's the third car I've owned in my life. It's going to be my last car. It's 19 years old. I put on 1,200 miles. And it's only got 60,000 miles on it. And so, but the dealer wants you to just go back and do all sorts of unnecessary things for this car, because that's how they make their money. Anyway, I digress. So we're working on this lithium metal battery. We may make it, we may not make it, but somebody in the world is going to make it. All right, so anyway, I talked about hydrogen. Now I'm going to switch gears in my last couple of minutes and talk about something that is totally different, stepping way back and looking at the big picture. And it turns out every economy in the world, and all the economists will say that if you want to increase the economic prosperity of your country and global competitiveness, you actually want to have more young workers, a smaller aging population. More young people, a smaller group of old people. You don't want the older people to get older and fewer young people. And so what is this? This is known as a pyramid scheme or a Ponzi scheme, right? And so the question is, if you look at what's happening today around the world, for example, in Europe, they're actually trying to get people in Europe to have more kids. I think it's Hungary or Poland. If you have 4 kids, you're tax-free for the rest of your life. I had a good friend, Pierre Dejean, and a Nobel laureate. He's since passed away, but I knew his wife, but he also had a mistress. He had a mistress for decades, and I knew his mistress professionally also. She was also a polymer scientist, and his mistress said that she got an award from France. She had, I think it was 4 children as Pierre Dejean's mistress, not as his wife. And she got an award for having French kids. But what does this mean? Does this mean we're going to 11 billion people and we're going to 12 billion and 15 billion and 20 billion? The world can't support that. So let's talk about population. Those of you who don't, I recommend this website. It's called Gapminder. It was founded by Hans Rosling, who's since passed away, but it's continued by his children who flank him. And this is an amazing website. In this website, you can put on the X and Y axis. This is a data thing you can plot. So I've done this. And so I wanted to see what's the correlation between the average income of a country and the average fertility rate, how many, whether you have a rising or falling population. And it turns out the average fertility rate, in order to break even, is 2.1 because of infant mortality and childhood mortality. You have to have, if 2 people make 2 kids, that's not enough. 2 people have to make 2.1 kids. All right, so this is in 1912, this is the United States. As the United States gets wealthier, the fertility rate goes from 7 babies per woman down to 4. Germany is in yellow and India is over here. Let me fast forward to the end in 2018. What you have is the United States fertility rate going below 2, so going into negative population. What you have is Germany going well below 2. And in many countries in Europe and in Japan, the fertility rates are 1.3, 1.2. So you have a very rapidly aging population and negative growth. But you don't have to be that rich, because India is actually hovering now. Where's India? China's over here. India is over here. India is about 2.3. Even though the average income in India is less than $8,000 per year. China doesn't count because they had one-child policies and other stuff like that, but there was no such policy in India, Germany, or the United States. And so what is going on? And what is going on is as people become wealthier, as they no longer, when they have children, babies today, if you're in a middle class and you have a middle class existence, you expect your child to grow up, survive childhood, and actually die at the age of 70, 80, 90 years old. And so when you expect that, you no longer have 8 kids or 6 kids, hoping that 1 or 2 survive to take care of you in the old age. And so what has happened instead is you're beginning to see, oh, you have 2 kids and you got to pay for their college education, and oops, they may come back and live with you later in life. And so there's a real incentive to have fewer kids if you're wealthier, because your Social Security is going to be derived from something else. Okay, so it's a natural birth control. You increase the wealth, and this is true of every society, every religion, everything. You increase the wealth, you increase the economic well-being, and the population declines. So, you know, in many rural areas of Africa and Asia, human power remains the dominant form of moving food and water. But now we have something. How do you leapfrog into the 21st century? Just as you did with telephones, instead of wires, you go directly to a cell phone. Well, with solar energy and cheap batteries, you can have irrigation, you can pump water, you can purify the water. And all of a sudden, you put in reach people who used to hold their own water from the local well, and this is what these ladies are doing. Or you can even possibly say you can get electrical 2 or 3 wheelers that will require running on solar power when they become cheap enough, instead of having people load up 100 kilograms worth of stuff on a bicycle and push the bicycle, which is what you see in many parts of South Asia and in sub-Saharan Africa. All right. How do we get to this point where we're going to say you can use technology to improve wealth, but you don't want to say we're going to have more and more babies and increasing population? And so you need to redefine wealth. Right now, wealth is defined by gross domestic product. Gross domestic product is defined by how much stuff you consume, make, and use. And so, you know, when you have one adult owning one car, the average light vehicle in the United States is one light vehicle per adult, you increase the gross domestic product. If the entire world aspires to the American meat diet and the American way of consumption, this is really unsustainable. And so it's not the stuff, it's really the quality of life. And we have something already called the Human Development Index, which consists of 3 things. It's the GDP per person in each country. It's the logarithm, because if you're 10 times wealthier, your life doesn't change tenfold. If you go from $50,000 to $500,000 to $5 million to $50 million income a year, it's not really changing as much as you might think. It's probably going downhill. In any case, let's define wealth to include not only longevity, but the quality of life, that you remain fit and active and alert, and you have security for yourself, your home, your family, everything else, your environment, your community, that you can have the possibility of educating and learning new things well into old age, and living comfort. These are things we care about. I hope at least as much as having 2 cars per person. And so if we redefine wealth instead of just GDP, that gives us something better to look for. Now, the universe is a very big place. very recently, we've discovered exoplanets. In fact, the discoverers of these so-called exoplanets were awarded a Nobel Prize recently. And so here's a picture of a galaxy that kind of looks like our Milky Way galaxy. And if this were our Milky Way galaxy, we'd be around here somewhere. And then you say, well, we're trashing the environment of the Earth. Would it be possible to, just as we went to the New World, Europe went to the New World, there were indigenous people there, but they kind of took over the New World. Can we colonize other Earth-like planets? All right, so this is the size of our Milky Way galaxy. And you can say, well, how much does it take to explore these, lots of 10 billion, presumed, estimated to be 10 billion Earth-like planets in solar systems in our galaxy. And so, even to explore a small fraction of that, you'd have to get out of the gravitational hold of our solar system. The way you do that is not through rocket fuel. You get it out of orbit. And in this picture here, you see that as the satellite whips around, you use the gravitational pull of right here, using that green planet. It just trails it and gets a little velocity boost, a little velocity boost, and a little velocity boost. So this is an animation of how we got Voyager 2 to escape out of our solar system. So if you optimize these so-called velocity boosts, you can actually get velocities up to 60 kilometers per second. So how long, and that's pretty fast. So how long does it take to travel 530 light years? That's 1% of the radius of our galaxy. And it's going to take about 2.6 million years going at this really fast speed. Okay. So if you want to explore, just a small fraction, looking for nice places to resettle, don't think about it, because 2.6 million years is a long time to be in a spaceship. And not only that, what you find, once you get to the new solar system, you can't use the same trick to slow down, because it's based on timing. And so what happens is you're going at 60 kilometers per second, whizzing by, and yes, you can land on a planet, but in a pretty violent way. All right. Now, in closing, I want to remind you of one of my favorite pictures. It was taken by the astronauts in Apollo 8, Christmas Eve, 1968, and it's called Earthrise. And in this picture, you see a beautiful Earth, and you see the moon. And on the moon, you look at this picture, and it doesn't take much imagination that the moon is not a good place to live. There's no liquid water, there's no air, there's no magnetic field to shield you from lethal cosmic rays. So you don't want to really be living and forming colonies on the moon. The astronaut who took this picture, Bill Anders, said, we came all this way to explore the moon. And the most important thing is we discovered the Earth. So since 1968, what we discovered is we are altering the destiny of the Earth, we humans. And if you look at this picture, you see this very desolate lunar landscape, you see a beautiful Earth, and you see black everywhere. There is nowhere else to go. And so this is our home, and we've got to take care of this one, because that's all we have. That I'll stop, and thank you.
Thank you so much, Dr. Chu, for that presentation. We have a tradition here at Colorado Law School of giving the first question to a student, and I'd like to honor that tonight, even though I'm going to be asking the questions. So our first question comes from my student Ryan Lolar, who is in our JD program. And this question has to do with the relationship between government, law and policy, and development of some of these technologies. And he wants to know how much effort you think government should put into regulatory and financing measures to speed adoption of environmentally friendly technologies, and how much governments can just leave adoption of these technologies to market forces?
Okay, great question. And so I hope people appreciate that we don't have that much time. We talked about our carbon emissions and things like that. And if we're, so if we're going to stay below, have a chance of staying below 2 degrees, I'll remind you, we have to go to zero emissions and negative emissions before the end of this century. By 2070, 2080, at the latest, we go to negative emissions. Okay, the private sector left to its own devices is not going to do this. Even with the UN agreements, we're going to go well above 2 degrees or 2.5 or 3 degrees, 2.5 degrees. And so you've got to figure out how to stimulate the private sector to actually move a little bit faster. That's tricky because most of the stuff is in the private sector and you have to build in certain incentives. If you overly subsidize things, it doesn't do it. So it's got to be very artful. But yeah, a carbon price is just the beginning, but that's really not enough. But here's the thing about stimulating the economy and even saying that there's going to be a carbon price in 10 or 20 years is that will drive lots of private sector investments. Just as, there's huge investments now in recognizing that EVs will become a major form of transportation in 10 or 20 years. And countries are beginning to say by 2040 or 2050 or even 2030, where they're going to start to outlaw internal combustion engines in cities because of the pollution problem, just like think of horse poop, then that will hasten it, okay? But there are other things. Certainly in the research, which is the public domain, I think the government should be funding research, but in the end, you've got to get the private sector to pick it up. The question about finance is a very good one because it turned out financial mechanisms like reverse auctions went a long way to lowering the cost of offshore wind and solar and onshore wind. And so the new financing mechanism that actually didn't require a government subsidy, a country would say, hey, you want to build solar on this land? What do you bid? And if you're a reputable, we have confidence you can do this, you can award contracts. And so these solar contracts are now going for less than 2 cents a kilowatt hour in very sunny places in the Middle East. No subsidy, but just really a lot of sun and profit for, but this is 2 cents a kilowatt hour contract, which includes the profit of the person developing this. It's a mixture of better technology, cheaper manufacturing, and finance models.
I'm going to assert my moderator's prerogative at this point to ask a question of my own, which is that you're a scientist, but of course you've also been a politician, or maybe we call you politics adjacent. I don't know what you prefer, given your role as Secretary of Energy. But in American politics today, as you're well aware, the facts don't always persuade. So I'm wondering what you think are the most effective strategies for communicating your conclusions about what must be done to avert catastrophic climate change to people that disagree and are less interested in some of the modeling, for example, that you've shown us tonight.
Great question. Yes, I mean, if you look at our experience with COVID, right? People saying masks don't work, they're not helpful. People dying of COVID refuse to. There are some people, you've heard stories, they're dying of COVID, they're testing positive for COVID, they have all the symptoms of COVID and say, no, I don't have COVID. and so how do you convince people that this is important? Even we've seen up close and personal that something has become politicized, and they think that the vaccines are dangerous, not to be trusted, right? And 40% of the medical workers, not the doctors, but the others, are saying, I'm not sure I want to be the guinea pig and take this vaccine. And it turns out, for the other vaccines, years before, and there was also similar resistance. Okay. How do you convince people? I don't know. The way you convince people in general is they have to trust you. And how do you build trust? You don't build trust by going there and saying, look, I'm a scientist, I know better than you, trust me. It's like saying, you know, I work for the US government, I'm here to help you. Trust me. No. So I think a level of trust has broken down in the United States and around the world, and it's coming into many factions. And so the things that build trust is you do things that are not directly associated with the issue, whether it's vaccines or climate change. You know, you go to the same kids' soccer games or something like that. You interact with them socially in a non-threatening way. Until we can start to do this and begin to actually talk to each other and trust people, trust so that say, well, I don't agree with you, but I'm willing to listen to you without my blood boiling on both sides. We've got a real problem. And we do have a real problem. And lecturing people does not work. And so, you know, I just finished as president and chair of the AAAS, and what we're doing is we're saying, well, if we go into local people who live in the community, been to interact with people in PTA meetings and, you know, other things, band and soccer and all this other stuff, and just start to re-socialize with people. I'm going long-winded, but let me one more story. When I got to DC, I wasn't actually viewed as a politician. You know, I never campaigned for anybody in my life. And so a lot of the politicians actually, since they didn't view me as a politician, would tell me stuff. And they said, both sides of the aisle, they said, you know, we no longer live in DC. We no longer hang around DC. Senate only votes Tuesday, Wednesday, Thursday. Why? Because even though you have a long term, 6 years before you have to run again, you're flying back to your home state on Friday and you're coming back on Monday. Because if you're not there and, you know, pressing flesh and showing your face, and you're living and raising your family in DC, the people who elected you no longer trust you. Okay, what does that mean? That means the people in DC are no longer raising families together. And so they're no longer interacting on a social level. And so then all of a sudden, it goes to tribal. It withdraws in little tribes. And that has happened in DC. So we've got a problem, you know, because we do live in a democracy. But if you can't have trust across the aisle, we've got a real problem.
I'd agree more. I'm going to try to combine a set of questions that we've gotten in the Q&A, and it involves some other emerging technologies that you didn't touch on. So, you know, free to address any or all of these. But I think the broader question that others have is how much you're willing to rely on some of these emerging technologies, or even technologies that we haven't conceived of as potential solutions to policy problems and problems like climate change. And how much should we be maybe relying on what's in front of us and available right now? And some of the technologies that people are mentioning are things like carbon recapture technology, things like, I suppose biofuels is maybe less of an emerging technology at this point, advanced nuclear. So I'm going to throw all of that at you and let you answer any parts that you like.
Okay, great. Okay, so advanced nuclear. So the new thrust would be, can you make really small modular reactors in a factory? So that you have better quality control, and you stand by thousands at a time. And so you get economy of scale by making more. The difference between a car company makes 5,000 cars and 500,000 cars is the difference between selling cars at $200,000. At $100,000, if you're only making 5,000 cars, you sell at a loss. The same car, 500,000, you can sell them at $50,000, $60,000. I mean, this was what happened with Tesla. It's an economy of scale. So if you make a small modular reactor that is passively safe. That means you lose complete control of everything, the cooling, everything. Walk away safe. It doesn't melt down. It doesn't contaminate. And so when our Secretary of Energy said, we're going to help companies in their engineering design, but that was a requirement. It has to be passively safe. And so there's a lot of money out there looking now in the last 5 years, because remember, you have a choice between fossil fuel with carbon capture or nuclear. Now, fusion may or may not happen, but you can't hold your breath on fusion. And so given that, it's kind of choose your poison, if you will. I mean, nuclear has some, spent fuel issues, fears, contamination fears, things like that. And the spent fuel, actually, there could be a solution. I'm a scientific advisor to a new startup company called Deep Isolation. And saying if you can take a spent fuel in a borehole, let's say a meter wide or so, you drill down a couple of kilometers, you drill sideways a couple of kilometers, you put it into geological formations that you would never dream of digging tunnels, because it would be too costly. Certainly you wouldn't dream of digging tunnels like in Yucca Mountain where people go in there. It's like the cost difference between manned spaceflight and unmanned spaceflight, right? And the risks and everything like that. But drilling a hole and drilling sideways is something the oil industry gave us, and they're very good at. And so you can do this, and you can put them in geological formations, even possibly in many of the reactor sites in the United States already, if you're willing to go a couple of kilometers down, which we know how to do now. So you can imagine this small modular reactor, the size of a meter or two, the core part of it. After 20 years, think of it as a battery. It's a big AA battery. You take the whole thing and you put it in a borehole and you ship it underground. Then you get rid of the spent fuel problem, the contamination problem. The passively safe is part. So people are looking at that. Biofuels. I mentioned how important it is to have liquid hydrocarbons. Very important for airplanes. You're not going to fly an airplane on methanol or ethanol. There's just there's not enough energy per unit weight and not enough energy per unit volume to fly an airplane. You're not going to have tailpipe capture in an airplane. So either you have negative carbon emissions to compensate for the airplane emissions, or you make the fuel from organic material that captured CO2 from plants while it's made. And so you can make it a net zero. In fact, you can make it better than net zero, because in any fermentation process, you actually have excess CO2, so you bury that. It's not economically viable now. Right now, we don't know. We can maybe make it competing with $200 or $300 a barrel oil, but not $40 or $50. So it's a matter of getting better at that. And that's why we're looking at all sorts of other things as potential other solutions, not a full solution for hydrogen, not a full, but better solutions. Electric vehicles will take a lot of the burden, but not all of the burden. And so there's that technology. What was the other technology question you had?
Carbon recapture, machines that suck carbon out of the air.
Yeah, plants are great at that. And so there are several companies associated. I'm on the board of directors of a carbon capture company, trying better, newer technologies, new materials to suck carbon capture from cement plants, steel plants, power plants, plastic plants. But the same technology you can use for sucking it out of the air. It costs about 3 times more to suck it out of the atmosphere than it does to get it from a coal or natural gas or cement plant. So your training wheels are capture carbon from a cement plant, okay? Because that's 3 times cheaper, and then figure out what to do with it. And then you drive the cost down of air capture. In the end, air capture is absolutely necessary. because that's the only way. Either we do it by plants and turn the plants into something useful and sequester the rest of the carbon dioxide, so it's partially nature, or you do it by man-made things, but that requires energy, and it's got to be really cheap energy, and it also requires a lot of land. That's something else not fully appreciated. We use a lot of land for agriculture. So, you know, who's to say which is going to work? We'll probably need both. We'll probably need recycling of plant material and stuff the excess carbon in the ground and suck it directly out of the air. By the way, we're going to go over 450 parts per million for sure. We'll probably sadly go over 500, even 550 parts per million. Now we have a little time window before there's really bad stuff. Already we're seeing really bad stuff. And we're, you know, at 410 parts, 415 parts per million. But there's a delay in the really bad stuff. Why? Because the greenhouse gas layer we put up there is trapping more heat. So the solar cycle is 11 years, but it's pretty constant. So the amount of energy hitting the Earth and getting through the atmosphere is fairly constant if you average over 11 years. But the energy leaving the Earth is less. So we warm up. But there's something delaying the warm up that people don't realize, but it's really easy to understand. The oceans are very cold. If you've done any snorkeling, you go 2 meters down and it gets really cold fast. And so it takes a long time to warm up the oceans. The upper surface deep ocean mixing takes a long time. And it takes about 50, maybe 80 years to warm up the oceans. So think of a glass with ice cubes in it. Heat is coming in, but it kind of stays cool. After you've warmed up, okay. So it's going to take a while. So the damage we've already done won't be fully seen for at least 50 years, probably 100 years, which is tragic. But that, and thermal inertia allows us to say, oops, we're at 550 parts per million. The real damage is much worse 50 and 100 years from now. Suck it out of the air now before the oceans warm up. Okay. So there, but you know, that doesn't mean we should relax. We got 50 or 100 years to figure this out. No, we've got 50 years to go to zero carbon emissions. But after zero carbon emissions, we actually have to reverse it. Because so we're not in a good position, and time is running out. And so and the really scary thing is the stuff we've seen in the last decade. I did not think I would live to see. The violent weather, the forest fires, the droughts. I thought they were 30, 50 years away, but they're here now.
Sadly, time is running out for us tonight as well in this program, but I want to thank you so much for inspiring / scaring us into action. Our wonderful students are eager to partner with our friends across campus and across the country in the sciences to work on exactly these issues. But thank you so much from everyone here at Colorado Law for joining us tonight for the Schultz lecture. We really appreciate it.
My pleasure. Thank you for having me. All right.
Good night, everyone.
I hope I didn't scare everybody too much. I mean, look, you can't give up hope. If you give up hope, you then say, I no longer care about my children or my grandchildren. Right?
So we'll keep working.
You keep working, and we all keep working. All right.
Keep working.
Bye
Thank you. Have a good night. And everyone, thank you again for joining us. And we hope to see you at future events.
Thank you. Bye.
Bye.